Hello everyone, it's Lord Tony again, and I'm here on what is apparently my most popular YouTube video in years, the Wordle Peaks Auto Solver demo video, because not only did I get two comments on here, one of the comments is actually from the guy who created Wordle Peaks, so we're gonna lean in hard on this one. The other comment is from somebody else who actually wrote their own Wordle Peaks auto solver. And it looks like they've exhaustively gone through the entirety of the word list and, tested all of like their strategy on each word. So it looks like their strategy probably opens with the right word one time, as I imagine every strategy would open with the right word one time if you went through all of the words and brute forced it. Uh, and yeah, he listed out his numbers here. So what I'm gonna do is I'm just gonna code review the my own Wordle solver and kind of talk through the algorithm here. We're going to reverse engineer something I engineered to begin with. And so what I've got here is an HTML file opened in Notepad++ with some sort of Halloween yellow, black, and orange color scheme because I'm an absolute madman. I suggest you do all of your JavaScript coding like this. So yeah, I've got my style tag that turns out I'm not even using. Got my header. Then here at the bottom, I've got a body, and basically, I've written my own print statement. I've written my own print statement that just appends, like stringifies whatever text you pass in, and appends it to the DOM. So now I've basically turned my browser into a console that I can use for JavaScript. But yeah, the rest of this is just inline JavaScript inside the script file. I don't have it spaced out properly because, why bother looking 3 inches to the right when you can just push it all up against the left-hand side of the screen? So with that, let's kind of start from the main function here. So what I've done to answer that brute force question we've got here, let me just read this out. Hi, I've created my own Wordle Peaks solver, not really a solver, but more of a suggestion tool for people stuck. Because we both use different methods, I'm curious how your method compares to mine when it comes to how many guesses it takes for each answer to be solved. With mine, it guesses given only the actual answer set. Yeah, so he's done what I thought, taken the actual answer set and gotten the answers for it. So I'm doing that same thing. This is the entirety of the answer set, just ripped out of Wordle Peaks. And what I'm going to do is I changed my program to where instead of an auto solver, it just kind of counts how many steps it took to end up getting the answer. And in the actual Wordle solver, it turned out the ideal opening based on my algorithm was the word null. So I passed that in as the first word, and recurse through it, count everything, and if it took one turn, it adds something to the ones. If it took two turns, it adds something to the twos, then threes, then fours, and then I threw sixes and sevens on there just in case anything went over. And then I just kind of iterate through all the properties in that results array, and iterate through the properties of that results array, and then just spit it out on my fake console here. So here's what we got. We run the algorithm, and then it spits all that stuff on the screen. So apparently, checking this, I seem to have even done better than somebody who got to this problem before me. So this made me intrigued. Like maybe I stumbled upon a pretty good algorithm for this. So yeah, he's got 2 that solve in 6 words and a few that in 33 that solve in 5, whereas mine I've got a couple that solve 11 that solve in 5, none that solve in 6, and none that fail. So pretty good stuff there. So let's actually analyze what my algorithm is. So the idea, let's pop open Paint. We're using Notepad and Paint because I'm cool like that. Oh, too much programming. I try to type the word paint and I end up typing the word print. All right, so the idea is this. So let's say we've got 102 words in our word list, okay? And each of the words is like, 5 letters long. It might be, I don't know, it might be the word poops or something. You don't know. I bet that's on the word list. As a matter of fact, let's actually check for that. The word poops is not on the word list. Okay. Well, it's not every 5 letter word. But yeah, so let's say you got 102 words. We actually have like over 2,000. And so what happens is this first letter, it's either going to be in the top half of the alphabet or the bottom half of the alphabet. And so I thought originally, okay, your ideal word is just M. And that would be like, cut the alphabet in half. But thinking about this, okay, because your first letter, it'll either be, half the letters are above M, half the letters are below M, and occasionally the first letter of a word is M. So you would cut it in half. You would get like, I don't know, maybe 2 of the times you'd have M as your first letter. You'd get 50 on the bottom, 50 on the top. And you're effectively doing a binary search of just that letter space by putting M as your first letter. Same with all the other ones. But then I thought that assumes that there's equal probability of all of these letters being the same. So what I did instead is I went through the entire word list and I just counted up. I counted up for every letter I went through, and I'm like, okay, for every word in the word list, for every first letter, how many of them are greater than A? How many of them are less than A? How many of them are greater than B? How many are less than B? Or B. Yeah, yeah. So eventually, I came up with the pattern. I think it was LLMLM. So that's like the ideal word and or like the ideal pattern. If you could type that in, that would cut our word list in half, or as close to half as we could. Like let's say there's like 48 words on top and 50 on the bottom. So when you subtracted these two from each other and took the absolute value, you get 2. So as far as like low scores, L is the lowest at a 2. That would most likely cut the word set in half for that letter. And then I just did that for every letter going through. So now comes to the algorithm. So now I've got my ideal split for this given word set in its entirety. I found that split by just counting up all the letters. And now what I want to do is I want to find an actual word in the word list that's close to that. So what I did is I just went through every word in the word list and kind of scored it up. And the word I found that was the most similar was knoll. The way I'm detecting if it's the most similar is I'm basically taking the ASCII value of that K, the ASCII value of that L, and subtracting, one of them from the other one and taking the absolute value of that. So let's see, A, B, C, D, F, G, H, I, J, K, L. So, this is 1 off of L, L, M, N, M, N. So this is 2 off, M, O. Yeah, so O is 1 off of M, and then this is 0 off of L, and L, M. Yeah, and this is also 1 off. So you end up with the word knoll having the low score in the word list of 6. So that's how I decide the best word for the opener. And then I realized, like, what you do is you feed that in, and then you feed that in, and now the screen. Let's see. Here's my application. So I feed in the word knoll here. What I've done is just in case a word better than knoll shows up just randomly in the word list, this code won't actually have to change. This code will have to change where I copy paste in the word list, but this code down here that chooses the best word won't have to change. So what I do is I call that recursive function, because there's only going to be like 6 or 7 turns, and this enters my guess. Now this piece of code right here, where I enter the guess, this writes some other functions I have, like it basically takes your guess, iterates through the guess's length, and then just like presses those keys and then presses enter. And those are abstractified away as this right here. So one trick for if you want to be able to like wait on a set timeout is you can wrap it in a promise like this. So what I did is using jQuery, I basically find that the key I actually want to press ends up matching this pattern. And if it's the enter key, like if it's the enter key, I basically just straight up press the enter key. And then this pattern here is for all the keys that aren't the enter key. Because, if I say if it contains, if I try to type the letter E, if I say, it contains an E there, well, the problem is enter also matches that query. So I have to specifically say, if you're not pressing enter, you have to add that not wide thing on there. So that way it won't actually click the enter key unless you specifically tell it to. But now doing this whole wrap thing, I can just press keys and have half a second in between those keys. And once that resolves, then I can use await on it with some advanced JavaScript tech here. So yeah, that's basically it for pressing the keys there. But then the next piece is I have to find out how to score the I have to find out how to like score the output. Like once I put in my guess, I get the output from the game, and that is each row, each guess row is one of these. It has a tile row class on it, and I want to grab the nth one of those tile row classes. So if it's my first guess, like if that I comes in as my first guess, after I guess it, I want to look at the very first row. And because the nth of type is 1 indexed, and I've got my junk 0 indexed, I have to add 1 to it right here to get the proper scored tile. So I step through the row that I care about, and like the row I care about in each of the items on that row, and I peel out the output from that. If it's telling me that my letter comes before theirs, or I need to go up in the alphabet, I just throw a U in there. If it has after, that means I need to go down in the alphabet, so I throw a D in there. And if it's equal, then I say, hey, it's equal. Now with equal numbers, coming back to our little paint drawing, yeah, we'll get around to that. So yeah, then what I've done is now for each of those letters, there's going to be 5 of them. It'll say like up, up, down, equal, up, or something like that. Those are my directions. So now I prune the list. So I basically trim out the like all the chaff in the list. I rip out all the words that are not possible based on this configuration. Like everything that doesn't match that gets pruned out of the list. So if it's equal and my particular guess letter does not equal the particular word's letter, then I false out. But yeah, I prune the list, rip everything out, and make a copy because I like functional programming. Then what I do is I find the ideal split. I should definitely be consting these out. Yeah, I find my ideal split again, and that's that algorithm we talked about here that turned out to be LLML in the full word set, but now I just run that algorithm again on the pruned word set. So I find another ideal list, and then find the word in that list that's the closest to my ideal list, because unfortunately LLMLM will not be accepted as a guess. So do that same sort of thing, grab my ideal split out of the remaining pruned words, and then pass it back, or find the best word based on that ideal split, passing in, the pruned list and the ideal split. And then I recurse again, iterating my guess count by 1. And that is the entirety of the algorithm. So in order to again have a satisfying ending to this story, I'm going to break us into Wordle Peaks and watch it solve today's. So null, again, that's the first guess every time. So it pruned the list, and now it thought that word would cut the list in half the best. And then it thought that word would cut the list in half. And now there's probably only 1 word left in the list. Yeah, so this is one of my 4 guessers. And as we found out, there's going to be 500 out of that original word list that ends up getting solved in 4 guesses. So time to share this with my buddies again. Thanks for watching, and thank you for commenting. It makes my dopamine go up. Anyway, I will talk to you later.